Okay, so in this lecture, we're going to cover section 2.6. This is in this section, we're going to introduce this idea of the idea of a horizontal asymptote. And a horizontal asymptote is just it's involves looking at the behavior of a function as you go out towards positive or negative infinity. That is, you go very far away from zero, either in the positive direction or negative direction, or maybe both you want to consider. So let me share my screen so we can jump into the material. So oh, this is not the right one. Here, okay. So we have, so as I said, this is horizontal asymptotes. And before we can talk about horizontal asymptotes, we need to talk about limits at infinity. So a couple sections back, we introduced limits. We talked about them from an intuitive standpoint. We tried to make sense of what they were intuitively, and then we formalized limits rigorously and mathematically. And we talked about taking limits to some number. So we let x approach some specific finite number, and we saw that the limit of the function. So let me write this out actually. So we made sense of the following symbols. We made sense of this um, limit of f, limit as x goes to a of f of x, and we define this in terms of we gave a precise epsilon delta formulation of what these symbols mean, and we saw that this could equal, say, L for some number L. It could be either positive infinity, it could be negative infinity, or it might just not exist at all. And there's several ways that a limit can fail to exist. And when in these two cases right here, the positive or the negative infinity, we said when this limit was either positive or negative infinity, we said that the line. So let's draw these out. We said that the line x equals a is a vertical asymptote. A is a vertical asymptote to this function. So that means when you get very close to a, as x gets closer to a, the function either goes off to plus or minus infinity. So for example, you could have, let me see, you could have something like, ooh, you could have something like, this is terrible. Let's see. So this would be 1 over x. This is the graph of 1 over x. And you can see that the limit as x goes to, well, in this case, you do need to distinguish between approaching a number from either the left or the right. I didn't do that over here. You need to distinguish between left and right hand limits. When you approach x 0 from the right of 1, and you consider the function 1 over x, this goes off to infinity. But when you approach 0 from the left, you get negative infinity. And now horizontal limits are going to basically be it's kind of like the reverse situation. In this case, x is going to approach infinity, but f of x is going to approach, x is going to either approach infinity or negative infinity, and f of x is going to approach um, some finite number. So it's kind of like the reverse situation. And you can have different limits depending on whether you approach positive infinity or negative infinity. And this kind of due to the fact that there's this process in mathematics where you take a space and you so-called turn it into a quote unquote compact space. So the real line is not compact. It's not like it's unbounded, right? The real line is unbounded, so it's not compact. Of course, I haven't said what compact means. It's a kind of a technical topological idea, but there's this process where you can take a space and you can compactify it. You can make it compact. So in other words, like if you have the real line, you have zero, and then you all the way out here you have negative infinity, and all the way over here you have positive infinity. This real line keeps going, right? Basically, what you do is you just imagine that these are real points actually, and you glue them together. So you glue positive and negative infinity together. Whoops, to get a circle. So the compactification, one compactification of the real line is to glue, quote unquote, glue negative infinity and positive infinity together. So you kind of like imagine your arms are infinitely long and you can reach all the way out to positive and negative infinity. You grab, you quote unquote, grab the endpoints of the real line, which there really aren't endpoints, and then you just bring them together and glue them together, and you get this infinitely large circle. But as a this will be a compact space actually. Um, in a sense, it's infinitely large. And so now like you have this glued point right here where you have at the top you have negative infinity, and when you do this compactification, you're actually identifying these 2 points. So now you have this like these 2 points are the same, and you can approach uh this point, this glued point right here. So like you're gluing these two endpoints to get the circle, which I've drawn. I have for obvious reasons drawn small because it's just easier to represent it. This point where you glue them, and you can approach the point from left or the right. So that's why we have to like when we're considering horizontal asymptotes, you need to look at the limit as x goes to plus or minus infinity, kind of for this reason here, because you can there's like two ways to approach infinity, either like the positive direction and the negative direction in a sense. It's kind of weird. But so before we can, so in other words, what I want to just trying what I'm trying to say is that before we look at horizontal asymptotes, we need to talk about limits at infinity, and then we'll be able to easily define what an asymptote is. So the best way to figure out what an infinite limit should mean is to look at a concrete example. So let's consider this function right here. And I mean, intuitively, um, to figure out, so what we're trying to do is, well, this is what we want to do. Let me phrase it this way. Want to make sense of the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x. We want to make sense of these symbols. So intuitively, this just should mean that um, x goes to infinity, it gets larger and larger and larger. So you x is 1, and then 10, and then 100, and then 1,000, and then 100,000, and a million, a billion, etc. And you're plugging all these numbers into f of x, and you're looking at what number, if any, it approaches. And the same thing with negative infinity. You take -1, -10, -100, -1,000, -100,000, etc. And you plug all these numbers into f of x, and you look at which, if any, number it approaches or converges to. So let's look at this example right here. So we have f of x is equal to x squared minus 1 over x squared plus 1. So we have, let me just sorry, zoom in a little bit so we can look at this table. So we have, just to remind you, we have f of x is equal to x squared minus 1 over, was that what it was? X squared minus 1 over x squared plus 1. And so if you plug in 0, you're going to get -1. If you plug in plus or minus 1, you get 0. Plus or minus 2, you get 0.6. Plus or minus 3, you get the same value of 0.8, etc. And you keep going down. And so now you're considering in this table, you're considering either very large positive numbers or very large negative numbers. And you can see, so you're going off to plus or minus infinity, and you can see that this column right here is going to 1. So intuitively, we should say, oh, this limit right here, if I take the limit of this thing right here, it should approach either plus or minus infinity. It should approach one. So maybe we can say morally speaking. In this case, the limit as x goes to plus infinity should equal 1 plus infinity, and that should also be the same thing as x equals negative infinity of f of x. So both these limits should both equal 1. It's not always the case that you'll have that the left and the right hand limits going to plus or minus infinity are 1. They might be different numbers, which is perfectly fine. In this case, we get the same. So however we define these two symbols right here, however we define them, it should be the case that this is true for at least this example right here. So we want to formulate the definition in the correct way so that this happens. And so here's just a picture so you can visualize what's going on here. They gave us a plot. So here's the function, and you can see, yeah, this looks right. This is the right way to think about this, that the function when you go off to infinity, and you look at the height of the function, it's getting closer and closer to the red line, which is y is equal to 1. So it's approaching this line, y is equal to 1 in either direction. So yeah, as I said, we can express this symbolically as we can express it symbolically as this, and in general, we can use this notation. So we have this right here. So this is just the intuitive definition, and then we'll scroll down to the more rigorous definition. So we have f as a function defined on some interval, and we want the interval to be and this is just for some a. Let's just say for some a. It's not. It doesn't have to be anything specific. It can be any number a. As long as it's defined on one of these intervals of this form. It could be defined on maybe 1 to infinity, or maybe like 10 to infinity, or maybe like, I don't know, 10 to the 100 infinity, some really large number. It doesn't matter as long as it's defined on an interval of this form where the right endpoint is infinity, because you're going to want to think about x going towards infinity. So you want the function to be defined on an interval that goes out to infinity. So now if you're defined on such an interval for some a, you can write this, and what this means, and L for, let's also say let's say for some L, maybe it's 1, maybe it's whatever, it doesn't matter. For some real number L, and what that means is that as x can be made, the values of x can be made arbitrarily large, or sorry, arbitrarily close to L by requiring x to be sufficiently large. So as x gets large, if you want the distance from f of x to L to be some distance, say you want f of x to be within epsilon units of L, then all you have to do is say that x is sufficiently large. It's going out further and further to infinity, and you can guarantee that the distance between f of x and L will be that epsilon, whatever epsilon I give you. So it's gonna the rigorous definition of a limit of infinity is gonna involve epsilon. It's gonna be this epsilon formulation. So let's actually scroll. Oh, here's just some more notation. So this can be expressed as saying that f of x approaches L as x approaches infinity. I don't know if I actually explained that notation, but you can just use that notation for regular limits as well. Can be expressed as f of x, f of x equals L approaches L as x approaches A. And then just this is more general, and then you could take A to be infinity if you want. So this is just more notation. It's not meant to confuse you or anything like that. It's just more notation, and sometimes it's more convenient to maybe say use this than this. Um, so let's see. So here's just different ways of reading this notation. So it says the first one is that the limit of f of x as x approaches infinity is L, or the limit of f of x as x becomes infinite. So it won't be infinite, but it's like getting larger and larger, is L, or the limit of f of x as x increases without bound, is L. So these are just a bunch of different ways. And what we actually, so this is just an intuitive way of thinking about these infinite limits, but we do need to make these more precise. We're going to make these more precise and using a definition that a definition similar to the epsilon delta definition we looked at in 2.4 of um, this kind of limit right here. Limit of x goes to a of f of x equals L, where a is in this case a finite number. So we made that rigorous, and that's what we're going to do right now. So oh, here's some just examples. Here's like this is, x is going off to infinity, and x approaches this line L. So in this case, it actually at some point crosses through the line. So in the first example we looked at here, you might think, oh, okay, so it asks this number that approaches, like it can't cross through it, but or this line that it approaches as you go out to plus infinity or minus infinity, it can't actually cross through that, but that's perfectly conceivable. So like in this first example, you have that it intersects here. And this second example, it doesn't the second example doesn't intersect anywhere. In this third example, you have this oscillatory behavior, and this is like maybe like some sort of sine curve with like a dampening, like when we saw with x squared over we saw something like this. This was like it had this dampening effect. This doesn't have an asymptote, but it has that like when you graph this, it's bound between the parabolas, remember? And it kind of goes like this, goes like that. It's like dampened near zero. Um, this case though, you have this line and it just oscillates around. So it has actually a lot of intersection points. It's going to have infinitely many points. But it gets, as we can you notice, as you go out to infinity, it gets like it gets like trapped in some sense. This curve gets trapped. It has to hover around and get closer and closer to this line y is equal to L. So it's like attracted to this line in a sense, and it gets closer and closer to it. So these are, you can have a lot of different behaviors as you approach, as x approaches infinity. Of course, the function itself could go up to infinity. So for example, if you might not be finite at all. If you have, say, the parabola x squared, and when you take the limit, so this is f of x is equal to x squared, you take the limit of f of x as x goes to infinity, you could have infinity. So you could either have a finite number like L that you approach, or you could just be infinity as well. So let me just skip down. Oh, let me skip. Okay, so here's definition of as you go to negative infinity. And we kind of already looked at that. So the definition is not too much different. So now in this case, you want to be defined on some interval of this form, negative infinity to a. Before we were looking at this, but now you want to go out to negative infinity. That's what we're doing here. We're taking a limit as x goes to negative infinity. And again, this is just for some a. It doesn't have to, you don't have to be defined on any such interval for some specific a. It's just some a, and not maybe all of these a's. And then again, this is for some L, real number L. And it basically has the same meaning. It's not much different, the infinite limit. So let's go down to the precise definition. I'm going to jump ahead and then we'll cover all this material out. So let's see, where is it? All right, so here's the precise definition of a limit infinity. So we're going to take f is going to be defined on some interval a to infinity, and then this notation, which we have like an intuitive understanding of, means the following. So it has this more rigorous formulation. It means that for every epsilon, so any distance I give you, you can find a corresponding number n. So n could be n is usually some large number, and then epsilon usually some small distance. So epsilon represents a distance, and this is usually small, and n is usually some large number. And then so this no these symbols right here, the limit of f of x as x goes to infinity equals L, means that for every epsilon I give you, some small distance I give you, you can find a corresponding large number n, such that if x is bigger than this large number, then f of x will be within epsilon units of L. So you'll be really close to it. So it's a very, very similar um, formulation of the other definition of a limit. The only difference is actually this part right here. Before, we wanted x to be so close to some number a, but not possibly equal to a. In this case, instead of wanting x close to some finite number, this says that we um x x close to infinity. We want it to be close to infinity. So, as I said, n is usually going to be some very, very large number, and you want x to be bigger than this large number, so it's going towards infinity. So what this says is that the values of f of x can be made arbitrarily close to L within a distance of epsilon by requiring x to be sufficiently large. In fact, larger than this number n, and n is going to depend upon epsilon, just like delta usually depends upon epsilon. Usually I give you an epsilon, and usually you define delta somehow in terms of epsilon. And that's going to be basically the same case with this n right here. You're going to define n in terms of epsilon in some way. And so graphically what this means is the following. So we have this curve right here. So this epsilon right here, epsilon positive is given. So remember, this is like an epsilon game, right? With just like with the other definition of a limit, this is like a game. I give you an epsilon, and you need to find an n such that when x is beyond that n, when it's goes past it. So here's n, and then maybe x is here or somewhere even further out. Um, when you're that much closer to infinity than n, you can look at you have this line y is equal to L, and you can see that it's that the function, the graph of the function, the blue curve, is within epsilon units of that line. So if you have some line number L, you can look at um sorry, you can look at L plus epsilon. So it's like you just perturb the L a little bit, you push it up here a little bit to here, and then you take L minus epsilon, and so you're down here. You shrink the number a little bit by subtracting this epsilon. This will give you this band right here. And so when you are within this band, when x is over here, it will guarantee that f of x is between these two lines. This is going to be the right n, because remember, this is equivalent to, if you unpack this, it is equivalent to L minus epsilon less than f of x, less than L plus epsilon. So what this means is that if I give you an epsilon, you can find an n such that if x is bigger than n, then f of x is between L minus epsilon and L plus epsilon. And you can see from the graph that this n works, right? If you choose this n right here, in other words, this says that it's between the lines. Whoops, that's not how you spell that word. It's between the lines. Y is equal to L minus epsilon, and y is equal to L plus epsilon. And you can see that the graph is in fact between these lines right here. This line and this line right here. And of course, if you go outside of it, like say here, now if you're smaller than n, now you are suddenly outside that line. You're no longer um within those. So this would not be the right n to choose right here. It wouldn't be right to choose n here. You need n to be exactly here. You can choose any n larger than this n. You can like replace n by say an n right here, and you'll still get the conclusion that you want, that the graph is bound between the lines. So that's the rigorous definition, and this is just a way of visualizing this definition. And then okay, so now they're imagining that you choose epsilon to be even smaller. So take a smaller value of n, then you're gonna want to take a larger value of n, maybe required. You want to need to go out further to infinity so that you're trapped between, so that the function, the blue curve, is trapped between these lines, which are now closer together because you've chosen a smaller epsilon. All right, so that's the precise definition of a limit as x goes to infinity, and you have basically the same definition for x goes to negative infinity. The only difference in this case is that, again, you need to be on some interval of this form. So instead of a to infinity, it's going to be negative infinity to a. And this swaps right here because you want x to be smaller than n because you want to go to off to infinity, right? So in this case, there's a corresponding number n, and usually n is going to be a large, quote unquote, large negative number. It's going to be some large negative number. All right, so now, so that's that. Those are the precise formulations of infinite limits. So now let's talk about asymptotes. So asymptote is a pretty straightforward concept now. So we define a line L to be a horizontal asymptote to this curve, to the function or the curve f of x, if either one of these limits is the case. Either one. Maybe both are the case, but just at least one of them is the case. So in this case, this line y is equal to L is a horizontal asymptote. This line y is equal to L is a horizontal asymptote. So this is going out to negative infinity. This is going out. This one's going out to negative infinity. This one's going out to negative infinity. It's an asymptote. These ones are positive infinity. So as x goes to positive infinity, you get this asymptote. Same for the other two. And in this first example we looked at, we see that the line y is a asymptote. Y is equal to 1 is a horizontal asymptote because if x goes to plus infinity or minus infinity, the graph gets really close to the line y is equal to 1. All right, so now let's look at some tricks and techniques for well, let's see, actually here's another. Oh yeah, tan inverse has two horizontal asymptotes. So basically, if you have a graph with vertical, so here's a fact. Here's a more general fact. If f is injective, and let's say x equals a is a vertical asymptote, then y is equal to a is a horizontal asymptote of f inverse. And that's because like the when you take the graph of f inverse, you have to reflect it over the diagonal line. So you're a vertical line. Now and when you reflect the graph of the function, you reflect the asymptotes of the function as well. So a vertical line, when reflected over the diagonal line, becomes a horizontal line. So remember, the graph of tangent. Let me see if I can do these let's see, Wolfram alpha. Let's do a plot of tangent tan of x, and maybe put these together side by side. So you can see um, here at negative pi over 2 and pi over 2, you have vertical asymptotes. And then you have this diagonal line. Hopefully you can kind of see what I'm doing. The diagonal line goes off like this. So let me actually plot. And y is equal to x. And I plot vertical lines pi over, say, negative pi over 2. And x is equal to pi over 2. Let's see if that works. I don't think it understood what I was doing. That's weird. Why is that? Okay, so there's the diagonal line. What if I do and x is equal to negative pi over 2 and x is equal to pi over 2? Does that work? No, it doesn't work. But hopefully you can just see that the function has, now you can't even see it. There's pi over 2 maybe like over here and then negative pi over 2 over here. But those vertical lines, I was trying to like maybe show you. Maybe you can see it without me plotting it that way. Um, these vertical lines at negative pi over 2 and then pi over 2, when you reflect it over the diagonal line, they're going to become, when you reflect a vertical asymptote or vertical line, it becomes a horizontal line. So that's why I have this fact. Whoops. All right, so that means that tan inverse has horizontal asymptotes at pi and pi over 2 and negative pi over 2. All right, here's an example we looked at. Actually, well, this is not quite what we looked at. We looked at the limit of 1 over x as x goes to 0 from the left to the right. And you can do the same now. You can do a similar calculation where you take x goes to infinity and negative infinity. And you can just see from the graph, or you can just observe from calculations right here, that if x is large, then 1 over x is small. So like 1 over 100 is a small number. 1 over 10,000 is a small number. 1 over, I guess this is a million, is an even smaller number. So it's like as you go along, the height of the graph above the x-axis is shrinking, going to 0. And the same thing is true when x is a large negative number, you get 1 over x is a small negative number. So these limits are both 0. So y is equal to 0, the x-axis is a horizontal asymptote of the curve y is equal to 1 over x. So here's some more general facts, actually. If you have that r is a rational number, then this limit is always 0. So for example, an example of this is the one we already saw. The limit as x goes to infinity of 1 over x is 0. Or the limit as x goes to infinity of 1 over x squared is also 0. And now you have, what is this second statement? Oh, all right. So this is when x goes to positive infinity. Now for the negative infinity, you got to be careful because um, depending on what kind of rational number you're using, r to the x might not be defined. So for example, this limit doesn't make sense if r is equal to 1/2, because now you're letting x go up to infinity, so you'd basically be taking square roots of negative numbers. So you got to make sure that you have a rational number such that r to the x is always defined. And in that case, then you can conclude it's 0. But if you have like r to the 1/2, this doesn't make sense. It doesn't make even sense to take the limit as x goes to infinity. because it's not the function 1 over square root of x isn't even defined, so it's not defined. Well, that's a good point actually. So note um note. So this is with regards to the second point. Note, you have to be careful because 1 over square root of x, so r is equal to 1/2, is not defined on any interval of the form big infinity to a for any real number a. So, and remember, that was part of the definition to take the limit as x goes to infinity. You have to be defined on some interval of this form, right? But it turns out 1 over square root of x is not defined on any interval of that form. All right, so now let's so this is going to be a really nice fact, and it's going to help us do some calculations. So let me open OneNote so we can do this calculation in real time instead of just like going through the calculation in the book. So now let's see. All right, so what we want to do is this is example 3. So we want to take we want to compute the limit as x goes to infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. So the idea is so if you try to just evaluate this limit like just the way it is, you're not going to get a clear answer. So if as x goes to infinity, x goes to infinity, x squared goes to infinity, 3 times infinity will be infinity. So you have infinity minus 2 in the numerator. And what the heck does that mean? And in the denominator, you have 5 times infinity squared, or 5 times infinity, plus 4 times infinity plus 1. And so you just get infinities all over the place. And infinity is not a number, so there's no arithmetic of infinity. But there's a way of doing there's a clever trick that we're going to use, and we're going to use this a lot when dealing with limits of quotients like this. And the trick is, here's the trick. You compare the numerator slash denominator to find largest power of x, largest power of x, and then divide the numerator and the denominator by it. So in this case, you look at the numerator and the denominator, and in fact, in this case, they're just the same. It's x squared is the largest power of x. So, and that's fine. The numerator and denominator could have the same power of x. So what we're going to do is we're going to divide by x squared in the numerator and the denominator. So what you're going to get is you're going to get 3x squared minus x divided by x, and you have to do the divide in the numerator and the denominator. Otherwise, you're gonna end up with a different fraction. If you only divide the numerator by x squared, you're gonna get a completely different result. So we're gonna divide the numerator and the denominator by x squared. And now we're gonna now actually do the division. So x into 3x gives us 3x squared gives us 3. Minus x into x gives us 1 over x. And then x squared into 2 gives us 2 over x squared. And in the denominator, 5 into 5x squared gives us 5. Plus 4 and x and squared into 4x gives us 4 over x. And then x squared into 1 gives us 1 over x squared. And now I can use basically the limit law, which says that if you take the limit of a fraction, you can just take the fraction of the limits. So this is going to be me taking the limit of the numerator And the denominator, oops, 5 plus 4 over x plus 1 over x squared. And now just remember that fact. So remember fact. We'll just say that if if R is rational, then the limit as x goes to infinity of 1 over x to the R is 0, right? So here we have a 1 over x. So x to the 1 is rational, the rational power. However, 2 over x squared, so the 2 is a rational number. And the same thing in the denominator. So these underlying terms right here, when you take their limits, they're just going to be 0. So you're going to end up with, and then of course 3 and the 5 are constants, so they just stay behind. So it's going to be 3 minus 0 over 5 minus plus 0 plus 0. And of course that's just going to simplify to 3 over 5. So let me pull up the book again. So here's the exact calculation I went through. They actually did this. I just did this step and then jump from that step to this step. If you want to include this step right here, that's perfectly fine. You can distribute the limit over each term in the numerator and the denominator, and then take the limit. But it's not necessary. You can avoid that if you like. So here is a plot of the function right here. And see, we got 3 over 5. So 3 over 5, I guess, is this 0.6 is the same thing as 3 over 5. So this says that the line is the horizontal asymptote is 3 over 5. It gets close to it. In fact, if, as they note here, if you let x go to negative infinity, you're also going to get 3/5. So this, you can do the same exact calculation, this whole same exact calculation right here, but instead of letting x go to positive infinity, like we are here, just let it go to negative infinity, and you get the same exact number. All right, so now let's do another example. Okay, so this is example 4. All right, so now we have, so the question is find the asymptotes of f of x is equal to square root of 2x squared plus 1 over 3x minus 5. So, um, so notice in the numerator we have this x squared. We're going to basically do the same trick where we divide by some power of x in the numerator and the denominator. But we don't just have x squared here. We have this square root. So really what we have is, in a sense, x in the numerator, but then x in the denominator. So really the highest power is x. So first of all, we're going to look at the x goes to infinity. So x going to infinity means x is positive, which is good. So now we're take the limit of f of x as x goes to infinity. And that's going to be the same thing as square root of 2x squared plus 1 over 3x minus 5. And as I said, really the highest power when you compare the numerator and denominator is x, because you have, it's not just x squared in the numerators, you have the square root outside. Of course, no, I'm not saying, note, and this is sometimes a mistake people make. I'm not saying that I'm not implicitly using something like this. This is very false. Very false. I'm not implicitly using this to justify that x is the largest power overall. So now I'm going to divide by x, the numerator and the denominator. All right, so now um, when I divide x into, so now note on the side, because x is positive, you can say that the square root of x squared is equal to just x, right? So this x right here can be replaced by this square root of x squared, and that's good because then I can like simplify things a bit. So I'm gonna have 2x squared plus 1 divided by square root of x squared, and that's all over. Now I'm gonna just divide the x in the denominator, so I'm gonna get 3 minus 5 over x. Now I have a square root in this numerator and a square root in this denominator, so I can take the square root of the whole fraction. So overall, it's gonna be square root of 2 over x, sorry, 2 plus 2x squared plus 1 over x squared, all over 3 minus 5x. And now I can simplify by doing the division, or I can just, sorry, I can just do this division right here. So I get square root of 2 plus 1 over x squared, all over 3 minus 5x over x. And now I can just distribute the limit over the fraction. So I get limit as x squared goes to infinity of 2 plus 1 over x squared over limit as x goes to infinity of 3 minus 5 over x. Now in the numerator, I have a square root, and this, remember the square root function is continuous, so I can just bring in the limit, right? So this would be the square root of the limit as x goes to infinity of 2 plus 1 over x squared. Now in the denominator, I just take the limit, right? So 3 is a constant, so it stays behind, and then I have 5 over x. Well, we know that 1 over x goes to 0, so this is going to be like 1 over 5. Sorry, it's going to be like minus 5 times 0 if you want. You can write that. And now take the limit in the numerator, so the 1 over, this 1 over x squared goes to 0. So then I end up with square root of 2 plus 0 over 3, which is the same thing as just square root of 2 over 3. All right, so now, so there's the, I'll leave it to you to read just for the sake of time. There's a second part to this problem. So this is just considering when x goes to infinity, but now you need to, and this shows that so this shows that as x goes to infinity, f of x goes to square root of 2 over 3. So this implies that the line y is equal to square root of 3 over 2 is a horizontal asymptote. Now, what about, and I'll leave this to you, what about when x goes to negative infinity? You have to consider that case as well. Well, I'll just leave it at that for now. All right, so now let's go, let's see, there's example 5. All right, so I think there's just a couple more examples we'll go through. So this is example 5. So yeah, I'll let you read through the rest of that example on your own. So example 5, we want to compute the limit as x goes to infinity of square root of x squared plus 1 minus x. So for this one you need to use multiply by the conjugate. So we're going to multiply by the conjugate. So it's going to be overall it's going to be square sorry, square root of x squared plus 1 minus x times um square root of x squared plus 1 plus x. So you have a minus here, so now the conjugate means you switch the sign to a plus. When you want to take the conjugate, you switch the sign to a plus. And when you do this calculation, oops, what you end up with in the numerator is x squared plus 1 minus x squared. And then in the denominator, you end up with x square root of x squared plus 1 plus x. And the numerator simplifies a bit to just give you 1 over square root of x squared plus 1 plus x. And basically what's happening is um, this is going to be 0, actually. This is just going to end up being 0 because when x goes to infinity, x squared gets big and then you add 1 and it's a big number. You take a square root of a really big number, it could still be pretty big. And then you add a large number to it. So overall, you have 1 over a very large number, and that number is only getting larger and larger and larger. So you have 1 over a very large number, which means you have a very small number. So it's going towards 0. So let me just show you this picture. They gave a plot of it, and they basically say the same thing as I said. Notice the denominator of this last expression becomes large as x becomes large. In fact, actually, yeah, that's right. This number right here is bigger than x itself. That's a good observation, actually. So in other words, x is less than or equal to square root of x squared plus 1 plus x. So if x goes to infinity, this thing goes to infinity, and then 1 over something that's going to infinity goes to 0. Maybe I should write that down. So here's like a fact, I guess. Let's see if I can phrase this correctly. So if um there's a lot of cases. Let's just simplify it though. Let's just suppose f of x is a positive non-negative function. So like we have here, this is a non-negative function right here. And the limit as x goes to infinity. Actually, no, let's say it's strictly bigger than 0. So positive. And you know that the limit as x goes to infinity is infinity. Then the limit as x goes to infinity of 1 over the function is going to be 0. Of course, you don't need this to be the case. That is positive. I think if you just have something like, if you have if I think, yeah. Anyways, let me maybe try to reformulate it in a moment, but this should be hopefully intuitively clear. If you have a function that's never 0, and in fact it's always positive, and it goes off to infinity as x goes to infinity, then 1 over the function should go to 0. It should be getting smaller. When you take 1 over a really big number, you get a very small number. I think you can actually maybe generalize this a little bit. Let me see if I can. Let me just try writing something down. What I'm writing here is gonna be a generalization of. I think if this is not 0, x maybe in some interval a to infinity, right? Oh, and um, oops, let me fix that while I'm at it. Frozen now. That's great. here we go. Okay. So I think this is a proper generalization. So if x is non-zero, Jesus, okay, hold on. F is non-zero for all x in some interval, and the limit as x goes to infinity of the absolute value of x is infinity, then you can say that the limit as x goes to infinity of 1 over f of x is 0. So um I think you can drop this fact here that x is positive, but you just got to throw in these absolute value bars. So if you know the absolute value goes off to infinity, whether it could, so in other words, what this is saying right here is that the function either goes to plus or minus infinity actually. So if a function itself goes to plus or minus infinity, that means the absolute value of the function either goes to plus or minus infinity. But whether you go to plus or minus infinity, 1 over a very large number or 1 over a very large negative number is still going to be a very small positive or negative number, so it should go off to 0. So there's a fact right there. Let's see. All right, here's another example. Maybe you were starting to read this already, so I guess we'll just go through this here. So you have, this is a composition. Oh, I see. Okay. So they're kind of being clever here. So they want to take this limit as x goes to 2 from the right. But you can see that there's just really there's no way to evaluate this function, to evaluate this limit. However, if you introduce this variable t as 1 over x minus 2, then you can say then as x goes to 2 from the right, what happens to what happens to t as x goes 2 from the right? Well, we know that t is gonna go to infinity, positive infinity to be exact. But remember, as x goes out to infinity, remember the graph arctan of x, or arctan of t. I think it's up here actually, right here. As your variable goes off to infinity, so in this case we're just looking at t, not x. As t goes out to infinity, the graph gets closer and closer to this line, pi over 2. So that means that this limit down here should be pi over 2, because that is the horizontal asymptote arctan of t. So we can say, so this last line right here is true. So, or this equality is true because y is equal to pi over t. Well, pi over 2 is a horizontal asymptote of arctan. Screw that. Just tan inverse of t, which is the same thing as arctan. So that's why this calculation is true. So you have to do this variable substitution. To see that, it might not be obvious, but once you do that variable substitution, it's kind of clear, I think, hopefully. Again, if none of this is making sense, feel free to message me. Absolutely. We can schedule office hours. In fact, I'll probably make an announcement just to remind you that um you can email me at any time, and we can also schedule a Zoom meeting if you need to go over any of these topics. Yeah, so the variable substitution is t, so let t be 1 over x minus 2, which is this thing inside the arctan. And then you just note that as x approaches 2 from the right, t is going to go off to infinity, right? Because of how we defined t right here. And so this limit, the original limit is equivalent to this limit right here. So the limit as x goes to 2 from the right of arctan of this mess is the same thing as just taking the limit as t goes to infinity of arctan of t. And then this equation, this equality right here is true because y pi over 2 is a vertical or horizontal asymptote. Pi over 2 is a horizontal asymptote of arctan, and pi over 2 is a vertical asymptote of tangent. All right, let's see. So now the exponential function also has an asymptote, and you can see that from the graph. So you have that as x goes to a negative infinity of e to the x, this goes up down to 0. And that kind of makes sense because um, when you take, so when x is a negative number, that means, so if you take like, if you take, so if x is negative, that implies that negative x is positive. And so then when you take e to the x, you can write it as e to the negative x. And so negative e to the negative x is e to some positive number, which is going to be pretty big. When you can see that when you take e to some positive number, say 1, it's going off to infinity. But then you have 1 over some very large number. This is 1 over a large number. So that should go off to 0, which it does. You can see in this column, these are going off to negative infinity, and these are going off to 0. All right, let's see what else. Oh, so they want to just evaluate this limit. And just another variable substitution to try to, so we do these variable substitutions. We're going to actually do these a lot. There's going to be a whole method called U substitution for integration. And it's just a way of reducing a given problem to something simpler that we've seen already. So this right here, we can take this as an established fact right here. This is a fact. You can either like justify it by using the graph, or you can just justify it by using this table, or you can just take it as a fact. Like, I'm going to just take this as a fact that this is true. So if I give you a problem, try to use that fact. So for example, in this problem, we have the limit as x goes to 0 from the left of e to the 1 over x. So let p be equal to 1 over x. And now as, so if t is equal to 1 over x, then as x goes to 0 from the left, I should say, so it's a small negative number, t, which is defined as 1 over x, should go off to negative infinity, right? So as x goes to 0 from the left, I'm sorry, I keep saying right. T, which is defined as 1 over x, should go off to negative infinity. And you can just see that from the graph, 1 over x. This is 1 over x. As x go, if you get, so here's 0, and you get closer and closer and closer to 0, this line, this curve is getting closer and closer to going off to negative infinity, right? So then this limit right here, the original limit, is equivalent to the limit as t goes to infinity of e to the t. And now that's exactly this limit up here, but where t is replaced by x. So no difference though. So, and we know that for a fact that that's 0. This is kind of a dumb example, so this does not exist because yeah, the sine x just oscillates between -1 and 1 infinitely often, so it doesn't approach anything. Let's see. I don't think I really care about these a whole lot. I don't think anything like this is going to come up. Let's see. So I don't think you need to worry about that. I don't think you know where we're about that. And I guess that's it. So we already went over the precise definition. Here's some examples using the precise definition. You can read them if you want. Maybe see if there's an easy one. Yeah, okay, let's read through this one. So this is a limit that we've already mentioned quite a lot and used quite a lot. So, but we can prove it, this limit, by using that definition. So here's how it works. I give you an epsilon. You need to find an n such that when x is greater than n, the distance from 1 over x to 0 is less than epsilon. And so yeah, we can just assume that x is completely positive, right? Because we want x to go up to positive infinity, so that when you take the absolute value of 1 over x minus 0, if x is positive, you get 1 over x, and then you just get you get absolute value of 1 over x, and that's just the same thing as 1 over x. Because if x is positive, 1 over x is positive. And so we want this to be less than epsilon. So if you flip things around, that's going to be saying that x is greater than 1 over epsilon. So that's why should suggest to us that n should be 1 over epsilon. That's how we should choose it. And it's the right choice. Because if you assume that x is greater than n, which is equal to 1 over epsilon, then you can show that the absolute value of 1 over x minus 0, which is equal to 1 over x, is going to be less than epsilon by construction. So that's how you prove that by definition. All right, I think that's it. Yes.